Hello, everybody. My name is Halu. Welcome back to the series we're dealing with operating systems. In today's episode, we're going to be talking about the paging hardware problem. Now, again, the code, there's a lot of comment lines really. The code is quite short, but in order to fully understand the code and what we're trying to do here, maybe I'll just quickly do some theory and then we'll move on to that. So when you're looking at paging hardware, what does that mean? Well, we are just mapping logical pages into the memory. Okay, so first of all, let me break down all of this. So what does logical mean? Let's say you have a process. Okay, now the process is quite big. So what your OS does, it breaks down the processes into pages. Now each page will have something called a page size. So how this works is, let's say my RAM, it has like 4 slots, for example, something like this, right? This one slot is something that we called a frame. Each frame will have a frame size, and this will be constant throughout all of this. Let's say the frame size is 4. So 0 to 4, 4 to 8, 8 to 12, and 12 to 16. So this is ordered memory. Okay. Now, what actually happens is you don't get a set of consecutive memory from 0 to 16. Let's say I have a process called P1 and that needs 3 pages. I'm able to break this down into 3 pages, and that means I can break this process into 3 pages, which I can fit into the memory. Now, the page size will be 4, which is the same as the frame size. What I'm really doing is breaking down into the process into chunks so that I can store them anywhere, not just sequentially. And why is this important? Well, look, in your memory, right? It is hard. You might not always have consecutive memory allocated to your process. Okay, because that's not something that's going to be available all the time. So let's say I have 4 more blocks, right? 3 and 4. Let's say these 3 blocks is up some process using. Now these 2 blocks some process using. Now I need 3 blocks, right? In that case, what will I do? I will actually take this 1 block and these 2 blocks. So I'll take 3 total frames. Each frame size will be 4. That will be the amount of pages that I have, and the page size is also the same as the frame size. That means page 1 will go here, page 2 will go here, page 3 will go here. Now you might ask, hello, why does this case in the first place? Come, let's say if I need 2 blocks, why do I even have to go and put it over there? Let's say there is again 8 cases and I need some other thing here. I can just do these 2 and I can consecutively allocate these 3 sequentially to the process. Well, that doesn't work the same way, guys. That's where this problem comes. Let's say I have, okay, I'm going to erase this again, and let's say I have another 4 chunks of memory, 4 frames. Let's say there's another process, right, which takes up this storage right now. Okay, and then I have another process, and that process takes these 2. Now what happens is this process right here, let's just call this process X, this completes. So I'm able to get this part of the memory freed up. This process, however, is still going on. In that case, I don't have a sequential memory. I only have something like this, and that's where the pattern that we had before will come. So this is page 1, this is page 2, and page 3. Now this is not sequentially there. So how will the OS know which part of the process is where? That is where something called a page table comes in. Okay, page table. The page table simply states the frame number, okay, and the page number and the offset. So starting address. So how this will look like is, as we discussed, right? 0 to 4, 4 to 8, 8 to 12, 16, and then this will just continue 20, 24, 28, 32, and 36, something like that. Let's say. Now, how will the page table look like in this case? I'll say this is what frame number. Think about it. This will be frame 0, this will be frame 1, frame 2, frame 3. So frame 3, page number 1, and the starting address will be 12. Okay, and similarly this will be frame 4, frame 5, frame 6, and then frame 7. So page 2 is in frame 6, right? And then the starting address will be 28, and then the page number will be 2. Similarly 3 will start from 32, and then the frame will be 7. So this is what the page table looks like. Okay, so the idea between the paging hardware problem is to map this logical page requests into physical memory wherever that is available. So that will be randomized. That's what we're going to be demoing here. This will go into random places. We will populate this page table to tell you where a page is, and then go anywhere. Now when you're looking at this itself, when you're looking at this chunk right here, the page size is something that we told is 4, right? So even within this frame 3, you actually have from in page 1 you have 4 subsections, right? And that is something you'll have in these addresses. So 12, 13, 14 and then 15 will actually have parts of the page. So page size being 4, first part, second part, third part and fourth part will reside there. Keep in mind is that the physical memory always needs to be greater than the logical memory. Okay, physical should be greater than the logical. This is very, very, very important. This is not always the case in your operating system. In fact, there's a whole concept about virtual memory there. But in this demo, we are not going to include virtual memory. We just deal with this so that whenever I'm doing something, I make sure that there is space available in my RAM in order to fully fit this process. Okay, that's the only constraint we're putting on top of this. Now let's go into the code and see what this looks like. Okay, so I'm going to go read through all of this. This is going to be more of a code walkthrough only. So this is what I've just discussed, right? So summary would be to fitting the logical pages into the main memory, something that we told just to know. So things to know, logical pages are what your processor are broken down into, something that we talked about. Each logical page will have a page size, which is what one page is broken down into. Again, parts, something that we discussed. In the main memory, there'll be frames and each frame will be allocated with one page from the process, which means the page size and the frame size should be equal, something that we also talked about. Now, the size of the physical address should always be greater than the size of the logical address. Again, that is something that we talked about. Finally, we talked about what the page table is. That is just a data structure which keeps tracks of where certain pages are allocated to which frame. So what is the logic behind this code? Well, very simple. What we're going to get as input, we're going to get the logical address size, the physical address size, what is the page size, which is also the frame size, then the starting address of the memory page table. What does that mean? Actually, in this case, we're starting with 0, right? It doesn't have to be the case. We can also start with 2, 4, something like that also. So that will be the initial offset when you're trying to create this page table. Okay, so what are the functions that we're going to be typing? First of all is creating this page table, which is initializing an empty page table where we just tell which are the available addresses. We'll initially not assign them to any pages at all, something that you look at here when we go through the page table. I think that they deleted that, but if you rewind back and see, we'll have an address column in the page table. That is what we're trying to do, and we'll basically create an empty page table. That is what the create page table function does. Map page table is mapping the logical pages onto frames and populating this page table. Display will be nothing but displaying this page table, and get physical address will be a function that upon giving the logical address, we will be getting which frame and where it's located. Okay. Now, how all of this will work? First of all, we'll have a class called a page table. Okay, so this is that class. So what are we getting from this class? First of all, we'll get what the physical address size is, what the logical address size is, what the page size or the frame size is, and the starting address, something that we discussed. Now the pages will be nothing but logical address size divided by page size. Okay, that's the amount of page. Let's say my logical address size is 32. Okay, and then my page size is 4. There's totally 8 pages. That's it. Very simple division. Same thing with frames. We divide this. So let's say the physical address size is 64, for example, and the page size is 4. 64 divided by 4 will give you 16, right? Here we actually have to divide this by the frame size, but since the frame size is equal to the page size, we're just dividing this by the page size. Okay, now self.page size will be the same. That's something that we're initializing. The starting address is something that we're also getting, and the page table will be a list. It will actually be a nested list, but that's something that we are initializing here. We're also setting the logical address size so that we can use this whenever we want for the rest of the code. Okay, if you're able to understand this, let's go ahead with the create page table function. So what it does, so this is the page table format, something that we discussed already. You have the frame number, the page number, and the starting address, right? So this will be a row in the page table, and all of this will be inside this list. So that's why I was talking about a nested list. Okay, so initially we know what frames to be iterate from frame 0. What that means is when the frame is the 0th frame, that will be the starting address that we're providing. As I talked about here, this doesn't have to be 0 always. This can be any address that I give. So the page table will start from here to wherever that goes. So it can be 2 or something. So for the first frame, this will start from 2 or whatever number I give as the starting address. From there, we will keep incrementing it by the frame size. Frame size again equal to the page size. Therefore, we'll increment that by the page size. So address of the previous entry plus page size will give you the next entry starting address in the page table. Okay, the page number will be -1, indicating that the page has not been allocated yet. This is what I talked about before, where we're just initializing the page table, then we'll map that separately. Okay, so this is what the page table function does. If you're able to understand that, I'll show you what it looks like in code. Also, you have the create table. Okay, so what it does is for frame number in self dot frame. So what is self dot frame is the amount of total frames present. So what we're saying is if initially the frame is 0, what you're appending to the page table is going to be the frame number, which is 0 minus 1, which will be is not allocated yet, with the starting address. In any other case, what will you append? You'll append the frame number minus 1 along with this previous table's value, which will be minus 1 of minus 1, which will give you the minus 1, that is the last element of the last element in this nested list, which will give you the address of the last element. With that, you're adding the page size, thereby giving the new page table entry. And once you're done with this, you will just simply populate this self dot page table list, and that's what we're doing with this function. Now let's move on to the mapping part, which is actually quite interesting, and that's where you have to think a bit. So what we're doing, we're actually, the best way for you to demo this to your teachers or your lab exam is to use the random module. That's where things get a bit hard. So when I say, you know, we're just going to be allocating this to this here, rather than us just allocating to some specific part, since there are not other processes going on at the same time, what we will do is we'll randomly assume 3 frames, for example 1 2 3, or how many ever pages that we require, and we will assign that as pages. Okay, we'll just assume the rest is busy, something like that. That's why we're using random module. So we know the number of pages, right? We'll iterate through the number of pages, and for each allocation we will check which and all frames are available. Now how do you know whether a frame is available? Again, if it says -1 as the page in the page table, then that means that it is available. That's what we're going to be checking. From there, we'll pick a random page and we will just assign it over there. Okay, and then that's what we're doing here. And finally, and what this looks like in code, we'll go over there first. So again, frame numbers from that to this point, that is iterating over all the frames and then getting all the available ones. That is, you're checking the first index whether it's -1. That and all, what you do, you add these frame numbers into the list of free frames. From there, pick a random frame number and assign it to this page. Okay, so that frame will be assigned with our page. This goes till let's say I have 6 pages, right? So 0th page, first page, second page, it goes up to the 5th page. That's how that works. Okay, so that is what map table looks like. So this function called allocate will actually just use this map table function. Okay, so for every page starting from 0 to the number below that, let's say I have 6 pages, right? That's something that we talked about. So 0 to 5, just map it into the page table. That's what we're saying here. Now finally, get physical address. Now that's the last part that we discussed in the theory, right? So what we're doing, that is, given what the logical address is, we're going to find out what the physical address is. Okay, in order to find that out, what we need to find out, first of all, we need to find out in which page is that logical address presented. How do you do that? We simply divide it by the page size, right? Let's say I have a logical address is 27, which is page size of 4. If I just divide that, I'll say 3.75, right? So it is there in the third frame, and sorry, third page, and an offset of 3 is there. Okay, so because if an offset of 4, it go to the 4th page. Okay, so that's how we're trying to figure this out. So what we're doing here is, if you look at the function itself, we will find out the page number, and the page number is given by logical address divided by the page size. Correct? So if I give a logical address and you know the page size, you'll know approximately in which page this page number is located. Okay, and offset is going to be from that page starting address, how many parts do I have to move forward in order to find out what the exact physical address is. So you find out the page number and the offset also. Then what do? You iterate over the page table and find out which frame has been allocated with your page number. Once you're able to get that, find out that frame's starting address using the page table and add this with the offset. So that starting address in the page table will give you for the 0th part of the page only. From there, you go to the offset in order to get the logical addresses, physical address. Once you get that, you can just go ahead and return the physical address. If you're able to understand till now, fantastic. If not, maybe watch this again. But the final thing is just displaying, which is nothing but displaying our page table. Now, once we are, then this is just going to iterate through the page table list and then print everything out there. Now, once all of this comes together, this is where the magic happens really. This is what the driver code looks like. So you get the physical address size, logical address size, page size, starting address is input, something that we talked about. Now just go ahead and page table will be the name of the variable there, create an instance of the page table class with all of these, and then call the create table function, which will create an empty page table. Now before the allocation, just display what the page table will look like. Go ahead, call the allocate method, which will allocate all of the pages, and after allocation again display what the page table looks like. Once that is there, get a logical address as an input. Okay, and then just go ahead and find the physical address. Now, when you're looking at this part right here, what we're saying is, let's say the logical address size is 32. That means from 0 to 31, you can enter any logical address. From there, we're going to go ahead and find the physical address. In order to find the physical address, what are we doing? We're taking the logical address. We're finding out which page that logical address belongs to. That's where we're doing this division right here. Right? From there, we're finding out what the offset is also. We're iterating through this page table. From there, we're finding out in which frame this is allocated in this page. We're adding that with the offset and returning the physical address. If all of this makes sense, let's go ahead and run this code and show you what that looks like. Okay, so I'm going to enter a physical address size of, let's say, 66. Okay, I'm going to enter a logical address size of 32. I'm going to, the page size will be 4, and it's set the starting address to be 2. So from 2 till 66 it'll go. Okay, if I click enter, let's go ahead and see what happens. First, you can see a total of 0 to 15. 16 frames have been generated, starting from 2 to 62. So 62 to 66, 2 to 6, 6 to 10, 10 to 14, all of that goes. And this is what my page table looks like. Now the page number is -1 in all of these cases because it's not been allocated yet. After allocation, this is what it looks like. So I set the logical address size to be 32. So if I divide this by 4, there's going to be 8 total pages from 0 to 7th page. Let's go ahead and see if all of them is allocated. So 0th page I can see right here, allocated to frame 14. All of this is random, by the way. So its starting address is 58. Now then I have page number 4. That is allocated to the 12th frame. Page number 1 is allocated to 9. So 2 will be 5, 3 will be 7. 4 is already we saw. 5 will be allocated to frame number 1, 6 will be allocated to frame 2, and finally 7 is allocated to frame 8, and you can see rest of it is -1. So everything from 0 to 7 has been allocated properly. From here, let's go ahead and see a logical address, what this looks like. Okay, so I'm going to give the logical address as 27. Okay, and enter. What happens? First of all, the page number is 6. Is that right? Well, let's divide this. Okay, so 27 by the page size will be 27 by 4. What is the quotient? The quotient is 6. The remainder is 3. So the page number is 6 and the offset is 3. It's the third part of the 7th frame, 7th page. Okay, therefore we get that. So what is the physical address? So you get the page number there. You map this back to the page table. So 6 is located in the frame number 2. Okay, so what is the starting address of frame number 2? It's 10. What is our offset? 3. Add 10 plus 3, you get a physical address 13. So everything that we wrote in the code is something that we're able to see in the output as well. I hope you're able to understand this. I hope you're able to understand how we are solving this paging hardware problem. We're able to demo how we're able to create a page table, map things to this page table, and retrieve stuff from the page table, converting logical addresses into physical addresses. This is what is required for you from this problem. I hope you're able to understand. If you have any questions, let me know down in the comments. If this video helped you, hit that like button. Obviously, all of this code is there in the GitHub repository. Link to that in the description. Thank you so much for watching. I'll see you in another video. Until then, bye.